Hey everyone, a very happy Tuesday and welcome to our Arm Tech Talk series, which is the place to be for the latest and greatest in trends, technologies, and best practices from Arm and our ecosystem partners. I'm thrilled you could join us today for a fantastic Arm Tech Talk from Arm and our ecosystem partners, CoreAVI, all about supercharging functional safety and how you can enable this with their offerings. So I'm super excited to have the team from Daniel, Jay, and Neil, and the team from CoreAVI and Arm on the call today for today's webinar, giving you this insight. So before we get to today's really exciting topic, I've got a couple of little slides to go through. This is the usual housekeeping stuff if you've attended one of our Arm Tech Talks before. But if you want to engage in the conversation, you can tweet us or use this hashtag on LinkedIn, which is Arm Tech Talks. I think we've done now, this might be our 70th talk, or we're pretty close to 70 tech talks we've done, which is just awesome. So there's some really great content for you to go and watch on our YouTube channel. So make sure you subscribe so you don't miss any of the upcoming talks, and indeed all of the past ones are on there for you to go and watch and enjoy. There's hours and hours of content from partners and in our ecosystem and from Arm. And all of our upcoming tech talks will be on arm.com/tech talks. We're about to make a couple more live this week, so do keep an eye on that site. The ones that are coming up, ST is on the website, so you can go and register for ST's Tech Talk next week, which is about how you can accelerate your AI project development on STM32 MCUs. And then we have a fantastic talk from Arduino coming up. We're just finalizing the title of that, but we have a very exciting speaker from Arduino. I'll leave you to guess who that is. And then we have our final talk before the summer break from Digirum, an AI ecosystem partner. So really excited to have these companies coming up. But let's get to today's topic, right? Today, we're joined by three great panelists from Arm and CoreAVI. I'm going to quickly introduce them on this slide, and then I'm going to hand over to Daniel, who's going to talk all about it to start with, and then Jayan and Neil subsequently. Before I go through the bios from our speakers, if you've got any questions at any time from today's Tech Talk, please use the Q&A box at the bottom in the Zoom menu bar, and we'll get to those at the end. I'm sure we'll have plenty of questions for our panelists today on this really exciting topic. So today, I'm really excited to be joined by Daniel, who's a solutions architect in our automotive business unit. I'm also thrilled to be joined by Jayan from our automotive GPU, who's our auto GPU product manager from Arm, and Neil. Neil's joining us as well as the general manager of automotive and embedded at CoreAVI. So we're going to hear from them later, from Jayan and Neil later on. But now it's time to hand over to Daniel. So Daniel, thanks so much for joining, and indeed Jayan and Neil, but why don't you take it away with the first part of today's Arm Tech Talk?
Hi, Tobias, and thanks to all for joining. These are the agenda topics. I'm not going to spend too much time on this slide, but these are the general categories that we're going to dive in to a little deeper today. So this graphic, I think, illustrates or does a great job of illustrating automotive systems with safety goals. In the software-defined vehicle era, these can be considered as applications with safety requirements, right? So in this tech talk, we will focus on active safety systems. These include applications and application areas such as anti-lock braking systems. A lot of people immediately think of their IVI or digital cockpit applications, but more so or more modern applications like autonomous drive or automated drive and assist systems. So in this talk specifically, we will dive a little bit deeper into human machine interfaces for these systems and how important of a role they play in the vehicle. So this includes displays like digital instrument clusters, heads-up displays, and now you're starting to hear more about augmented reality heads-up displays or 3D heads-up displays. So these not only display traditional safety content like telltales or warning indicators, maybe gear position, but also indicators like navigation aids or the distance between you and the driver or the vehicle in front of you, or objects or pedestrians detected. So functional safety can be defined as obviously addressing unreasonable risk due to hazards, right, in the malfunctioning of a system. So we'll dive a little bit deeper into that. But before we do that, we wanted to address some digital cockpit trends, right, that we're seeing in the market, and these are nothing new, right? These are things that are disrupting the automotive industry for many years now. I think if you buy a vehicle today, the vehicle cockpit in a new vehicle is much different than a vehicle you may have purchased 5 years ago. And these are the most common trends in that vehicle digital cockpit disruption, right? So not only are vehicle displays going digital, right? Every new generation of vehicle, there's more and more displays. We've seen some vehicle designs with as many as 12 displays, right? And vehicle manufacturers are designing systems so they can be software defined, right? And gone are the days of designing ECUs that are fixed function. So applications are being consolidated, and much more of a focus is being placed on safety and security. Jayant probably has some additional value to add on this slide as well.
Sorry, I was just thanks, Daniel. I was going to say that we've seen some examples of pillar-to-pillar displays being used, and that means the functional safety content is not going to be just limited to some pixels reserved on a spot. I mean, the manufacturers and OEMs have got a real estate and real innovation and imaginative, capabilities to utilize that space and make that experience more user-friendly for the drivers and passengers. Over to you, Dan.
Yeah, thank you. That's a great point. So how does functional safety apply in vehicle displays, right? And previous generation systems, with analog displays, safety requirements existed as well. These were primarily safety, addressing the safety implications of communicating these telltales or warning indicators or gear positions that I mentioned. So current generation displays, the automotive industry re-engineered those very similar safety mechanisms required to ensure the integrity of the digital representations of those indicators. We'll dive a little bit deeper into the safety mechanisms in place in today's systems, but another safety HMI feature that falls into this category is like the reverse guidelines, or the guidelines on the reverse cameras. What this graphic is really designed to show is the explosion of data, right, that's being displayed in the cockpit. So you might ask the question now is, will the safety mechanisms for digital clusters and today's displays scale with the advent of exploding displays in the cockpit, right? I put some examples here, right? This 3D augmented reality display. Jayant mentioned pillar-to-pillar displays, but one thing that we haven't really talked about is the displays that will come with these advanced display systems, or I'm sorry, advanced drive and assist, and then trending is obviously the autonomous capabilities. How will those capabilities be addressed or communicated as far as an HMI to the users? So I'm not going to spend too much time on this slide. I think it's more of like a retrospective to show how digital clusters are designed today and addressing the safety mechanisms for those digital clusters, right? There's multiple approaches, and one approach that isn't even discussed on this slide is software rendering in a safety mechanism or a safety renderer for the safety content. There's really three approaches here. Is a software verification approach with a safety monitor, doing hardware integrity checks with specialized software as display output checkers are common in the automotive industry. So that's hardware specifically to do that safety checking. And then there's combined approaches, right? That's what approach C is as well. So again, I'll ask the question, will these approaches today for the safety mechanisms addressing the safety content for today's HMIs, will those scale? And my answer to that is no, right? So today's approaches are designed for simple HMIs, I mentioned, telltales, gear position, maybe some lines on the display. But safety content is primarily static in location, and the display output checkers today are designed to do that specifically, right? It's just to do checks for certain areas of the screen. And those display output checkers have proprietary APIs, right? So if you engineer a display output checker mechanism on one SoC, it's going to be different on another silicon partner's SoC, right? And the approaches of today don't scale well beyond 2D content, right? And so having bounding boxes around this objects detected, right, or on ADAS displays, or 3D guidelines, or animated or 3D telltales, those aren't addressable with today's technology, right? And having a GPU would help that. I'm not going to spend too much time on this slide, but this is really designed to show, kind of the trends in ADAS and autonomy, right? So automation features coming in vehicles today. And let's make no bones about it. The vehicles of today are becoming autonomous, right? They're introducing autonomous features, right? And the way to ensure customer confidence, right, in next generation systems is to have safe, safe HMIs that are designed with safety as the initial goal, right? And that's how or OEMs will drive consumer confidence, right, in the systems they are deploying. At this point, I'll turn it over to Neil Stroud from CoreAVI, and he'll take it over.
Thanks, Daniel. Okay, let's see if we can get these slides to move forward.
To set the scene, Neil, I mean, we've seen where the market is moving and what current approaches do we have, and we certainly know that it's not scalable. So the question we had was like, if it is the first time in automotive industry, can we look somewhere else and can we draw some lessons? And you and CoreAVI have pedigree in avionics and safe graphics. So can you please walk us through the lessons?
Absolutely. Yeah. And you make a great point, Jayan. It's there's definitely lessons learned that we can take from the avionics industry. And for those of you who don't know, CoreAVI has been in the avionics industry for almost 2 decades. And of course, when we think about avionics, we think of it as being very safe, right? We all jump on and off planes all day long, and thankfully, the number of incidents and fatalities is extremely small. So it's considered a very, very safe mode of transport. And of course, it's one that the automotive industry is increasingly looking at for lessons learned. More and more of the conversations I get involved in with tier ones and OEMs, they know our pedigree, and they make the exact statement. We want to get the goodness from the avionics industry and put it into the car, into the vehicle, and take that learning, that benefit. So there's no doubt. And we've been through a very, very similar transition in the avionics industry as well, that we're just beginning to go through from the instrument cluster and the cockpit to main controller. So you think about the older planes, it was mechanical dials showing things like altitude and speed, etc. The modern cockpit that you can see there in the picture is very, very different. So it's fully glass today with very rich displays, again showing the important information to the pilot, like bearing, altitude, velocity, terrain information, and of course head-up displays as well. All of which is very, very relevant in the transition inside the vehicle as well. So we can get a lot of good learnings from what we've done so far and transition those into the automotive domain. Now, of course, there are some caveats. The avionics industry is in a very different place from the number of units shipped, the form factors, and of course the price expectations. Avionics is a low volume, high value market. Automotive is the polar opposite of that. So we want these learnings, the automotive industry want these learnings, but of course we've got to take into consideration, what's the right price point, what's the right performance point, what are the form factors we're talking about as well, what are the thermals. So there are a number of different constraints that we have to work through as an industry to solve, to get them where they're going to be mass adopted by the automotive industry, along with the goodness that it can provide. So I wanted to spend a few moments talking about the CoreAVI software stack. Now, what I'll say first, of course, is we're collaborating very closely with the team from Arm on the G78AE GPU. And the benefit to the developer, of course, is as you integrate the hardware and the software together, is you want a joined up safety story. There's no point having the safety credentials or the safety artifacts from the hardware vendor, and then you try and integrate the software and there's a disconnect between those two worlds, or even in worst case a conflict. So as a developer, you get a joined up story from the collaboration between Arm and CoreAVI that we've done our homework. It's a long-term collaboration, and you can be sure that when you integrate an SoC with the G78AE GPU and the CoreAVI stack, it just works, and that saves you time to market. It saves you time to certification, and of course adds more robustness to your overall safety story. So let's spend a few minutes on the stack itself. So initially, I wanted to talk about the Vulkan SC layer. So everything we have today is based on Vulkan SC. Vulkan SC is a very, very rich and powerful industry standard API, SC being safety critical, but it's derived from the much used Vulkan API that's used in gaming and consumer applications, all kinds of different things. So it's a very established API. The standard for safety critical Vulkan was ratified over 12 months ago. CoreAVI chaired the working group within Kronos. It was a journey of about 2 or 3 years with other industry players that got us to that point. And of course, we use this as our baseline underlying software layer that interfaces directly to the underlying GPU. The great thing about Vulkan as well is that it supports not only graphics from a safety critical perspective, but also compute. So as we think about more and more GPU applications, AI with safety critical needs coming into the use cases, this really leads you towards Vulkan SC as that underlying layer, because it can deal with both domains, both graphics and compute. So then on top of that, depending on your application, I'm just going to highlight the box on the left here. So thinking about graphics applications, so in the automotive domain, we see a lot of OpenGL ES applications being used, of course, in the cluster, which is great from a traditional instrument cluster perspective. But of course, GLES is not safety certifiable. So as we see more and more rich safety content coming into the cockpit domain controller, that display that Daniel talked about earlier on, you need to move over to a safety critical API. And of course, you can go native Vulkan SC, but that's in a lot of cases a step too far as a single step. I see that more of a transition over a period of time, maybe 1 or 2 generations. So one option we have available to the developer is to move those OpenGL ES applications to GLSC. There are actually 2 derivatives of GLSC, again, industry standards, GLSC1 or GLSC2, and you can migrate relatively easily from that ES to that SC domain and bring your applications along, and of course, getting to safety critical functional safety while you go. Of course, then in subsequent generations, if you want to do away with that and go native Vulkan, that's of course an option, and that's ultimately what I see in the industry anyway in years to come. Is this GL layer will eventually transition to native Vulkan. We also have a couple of products as well which support video streams. So again, if you think back to Daniel's comments on the rich content that indeed is safety critical in the vehicle, things like reversing cameras, you've got a safety critical stream there, which you need to know is rendering correctly, because if you're reversing a vehicle, you're making decisions based on that feed that's coming to your eyes. So you need to be sure that's being rendered correctly on the screen. So safety, EncoCore and DecoCore are two products that take things like H.264, H.265 streams and display those correctly for a safety domain. So moving over to the compute domain. So as I said, increasingly we're seeing more and more safe AI applications coming in. So with the advent of autonomous vehicles, of course, this is of paramount importance. And to execute those workloads, we're seeing GPU being adopted quite extensively. GPUs are great for doing this because they're very good at doing massive parallel calculations, which is just what you need. So we have two products here: Compute Core, which basically does acceleration of BLAS and FFT functions, which of course are the underpinnings of a lot of AI systems, and that runs massively quickly on a GPU versus a CPU, and again is safety certifiable. And then an implementation of OpenVX, which our product name here is VK-Core VX, again used for things like computer vision in safety applications. And as you can see, all of those products all sit on top of that Vulkan layer and interface down to the GPU via that Vulkan layer, and then give you standard API interfaces up to the application. The final product I wanted to talk about is TrueCore. So this is a safety monitor, and I'm going to dig into this in a little bit more detail on the next slide. But essentially, you want to be able to check the integrity of the GPU, check it's doing what it should be doing, you haven't got any faults, and TrueCore allows you to do that actually on the go, on the fly, within the system. So you can monitor the integrity of the underlying GPU and know that everything's okay. The final product, which I kind of wanted to seed a little bit, which isn't shown on the block diagram, is SYCL SC. So SYCL, as we know, is a broadly used language and API that has been adopted across the industry. And very recently, we got together with CodePlay to establish a working group, again within Kronos, to take SYCL and do a safety critical derivative, again, which will sit on top of the Vulkan layer and give you access to all the SYCL functionality. Of course, that includes bringing across workloads from other languages like CUDA, and then putting those onto other GPUs and maintain the functionality, the capability, the performance, but also giving you a path to safety certification as well. So a very important step. The working group has just been finalized and is being chaired by CodePlay. So we're already on a path to getting that API worked on and ratified in the coming years. So you'll see products from CoreAVI over time as well. Okay, so I wanted to spend just a few moments talking about a very specific application where the industry and ourselves have innovated to solve a problem, which I think is very relevant for the automotive industry. It solved a big problem in avionics. So just looking at this top flow display pipeline. So you've got your GPU there going through the display controller, and then touching on the integrity of any safety system. So as I said, any safety system, you need to be doing periodic testing that the system is indeed functioning correctly, doing what it should be doing, and meaning you can rely on the results that it's giving you or the information that it's displaying to you. And how this was solved in the primary flight display within the cockpit was to actually put an FPGA in that display pipeline, and then use the GPU to generate patterns or from the application that wouldn't sit on the display area, but outside of the display area, and then have that FPGA check those patterns. And then if everything's good, then you're reporting that everything's good and you carry on. But if you see any anomalies in those patterns, the FPGA would pick that up and then flag that as a potential safety issue. And at that point, you can make a decision how you want to deal with that information. Do you want to go to a safe state? Do you want to test again? Do you want to light up an alarm on the panel to say something's not quite right? So it worked very well, but obviously there's a significant overhead there, both from a hardware and software perspective, because you've got an extra piece of silicon on the board that's taking power and generating heat and making a bigger board. You've got additional software there as well that you've got to generate those test patterns as well. So if you think about within avionics, every square millimeter of physical space matters, every milliwatt of power matters, every gram of weight matters. So what did we do? So we actually managed to replace the FPGA and generate this test capability through a product called TrueCore, which I mentioned on the previous slide. And the philosophy is the same. It generates test patterns, but it's all done in software. So you can actually trigger periodic testing of the GPU from the application. It fires off known test patterns into the GPU on a cadence that's defined by the application. And you're testing the integrity of that GPU. So you can go off and again, depending on how the GPUs are architected, you can test that GPU and know that it's working correctly, and of course eliminate that FPGA. So this is very, very relevant for the automotive industry, again, where it's very cost sensitive, but also the same factors apply, where you've got to reduce the form factor, reduce the thermals, etc. So this is very, very relevant as we get into the kind of the cockpit domain controller. So TrueCore is a very powerful capability within the CoreAVI armory. Okay, with that, I'm going to hand off to Jayant.
Thank you, Neil. So we have seen even in the journey of avionics industry, how GPU was central to the solution of safety rendering or safe rendering. And with that, then we can move to the GPU that comes from ARM, which is first GPU, Mali G78AE. Let me take you through the G78AE highlights. So it is the purpose-built GPU for automotive use cases. We designed the GPU, followed ASIL Delta systematic process and ASIL Beta for diagnostics. So it simplifies software and system level certification, and as such reduces time to the market. It is the only Mali GPU with real hardware separation and hardware virtualization that ensures true freedom from interference, and that means there are no shared resources between partitions. I will come back to the issue of hardware separation and partition in subsequent slide. But last but not least on this slide, Mali G78AE is a very highly scalable GPU. You can configure it from 1 shader core to up to 24 shader cores, and that means you have performance of up to 6 TOPS and 1.5 teraflops in FP32. It can be used from a single display instrument cluster to multi-domain controllers, and it has been selected by leading players in ADAS and digital cockpit segment. Some of the partners have received the engineering silicons in 2022, and mass production is expected in 2023. Next slide is more elaboration of the highlights that I was talking about. The only point on this slide I would like to grab your attention to is that on top of the hardware separation and partition, up to 16 virtual machines can be supported for efficient time-sliced virtualization. There is flexible partition, which provides configurable workload isolation. Again, we'll come to that in subsequent slide. And this kind of partitioning architecture avoids single point of failure and also ensures robust freedom from interference. We have achieved 2 certification of hardware in 2022 and are on track for software certification in the second half of 2023. So next slide, please, Daniel. Yes, so with all said in the previous slides, a picture is worth 1,000 words. So this is a view of what Mali G78AE GPU can do or accomplish. If you look at this platform row, this is one GPU which has been partitioned into 3 mini GPUs, and each one of the partitions can be considered as a fully independent GPU. So in this instance, we have got 3 small G78AE GPUs. One of the partitions is reserved purely for safety critical workloads that are being executed on real-time operating system, and other 2 partitions are reserved for quality managed workloads. In this example, we have said one workload is running on Linux VM and the other one is on Android. And using the same GPU and 3 partitions, you can render, in this example, for up to 4 displays, and same GPU is being used to render safety display as well as quality managed content on the other display. Next slide takes us a bit more in detail on the concept of flexible partitioning. So this is a new approach for autonomous GPU workloads. You can configure your GPU as one GPU for a single workload, and then you can use it for quality managed workloads or for safety workloads. In the second example, we have here flexible partitioning, which separates workloads. So again, as I said previously, we have partitioned this GPU as 2 fully independent mini GPUs, one of which is being used for quality managed workloads, and the other partition or mini GPU is being used for safety critical workloads, in this case, cluster instrument and computer vision. Now, taking the same example a little bit further, what we have in this example is, yes, we have got 3 partitions, but in the case of first partitions, we also have got instances of virtual machines that are running on top of this partition. And that means you have quality managed workloads and yes, quality managed workloads that are being exercised through virtual machines, and then the separate partitions that ensure workloads such as safety critical, cluster and computer vision, and driver monitoring and HMI. And it's as far as the partitions are concerned, it can be configured at the boot time as well as at runtime for G78AE. Next slide, please, Daniel. So that was the value proposition of Mali G78AE. As you saw, we have achieved the safety certification on hardware in 2022. As far as software is concerned, this is the slide that takes us to that conclusion. Like, Arm has now partnered with CoreAVI as of 2019 to develop a functionally safe driver stack, and the EAC is second half of 2023. It is being developed to ASIL D and supports safety critical APIs and runtime tests for greater confidence. Once we have this safety critical driver, Arm will be the only IP provider to offer ISO 26262 certified hardware and certifiable Vulkan safety critical and OpenGL safety critical drivers at that time. And next is we are initially targeting auto-grade Linux for development, but it will be expanded over time to include key real-time operating systems in the marketplace. And for this purpose, next point, CoreAVI service business will also be available to support partners achieve safety rendering goals through objectives like OS porting or platform integration, etc. In terms of the safety driver stack itself, what we have is it supports open standard APIs such as Vulkan Safety Critical and OpenGL Safety Critical that Neil was talking about. It also allows for mixed OpenGL and Vulkan applications, and it can also run safety critical compute libraries on Vulkan Safety Critical API. And thing that is not mentioned on this slide is the same safety stack can also be used for safety composition. And As far as licensing is concerned, so either silicon partners can directly license the driver from ARM, or OEMs or tier ones can also license the driver from ARM. And last but not least, GPU is just one part of the story as far as ARM is considered in terms of offering safety critical IP. We have a whole portfolio of safety critical IP such as Cortex Auto CPUs, the MMUs, the GIGs, ISPs, and Safety Island. So our solutions are across the portfolio of products or of IPs. To conclude then, today's safety approach helps with rendering of what was formerly rendered on lights and steam gauges. Today's safe graphics has limitations. It will not scale to meet future requirements of digital cockpit and ADAS and AD when rendering focuses on user experience and becomes more of an art form. Avionics industry has traveled this path already, and there are lessons that can be adopted by automotive industry. CoreAVI has a long history to lead the way in creation of functionally safe software in avionics industry. And to that end, ARM has partnered with CoreAVI to help automotive partners transition from today's IVI to tomorrow's digital dashboard and ADAS and ED. Thank you very much for your time.
Thank you, Jayan, and thank you everyone for a great presentation. Really, really great insight into the applications of functional safety to the automotive industry and our collaboration from Arm and CoreAVI side. So really, really thrilled to have this, and thank you again for a great presentation. So now we come to a bit of Q&A. I've got a couple of questions for the panelists, but if any of you have any questions, please use the Q&A box in the Zoom menu bar. This is your chance to ask the questions to our panelists. We've got some great experts on the panel to help answer them. So I'd like to actually start with Neil first. If you look at the digital cockpit in automotive, Neil, what sort of complex safety content would you say that you could foresee being used in digital cockpit in automotive? And I'll start with Neil, but by all means, Daniel and Jay, please add in here if you've got any further insight from your perspectives too. But let's start with Neil on that question.
That's a great question. So I think if we look at the automotive industry in general, I mean, there's a trend that the old 0 to 60 time and those kind of things. We don't buy like that anymore. We buy based on the user experience of the vehicle, the look and feel of the vehicle, the experience when we sit inside the vehicle, and apps and connectivity and all those kinds of things. So consequently, the auto OEMs are investing huge amounts of money on that user experience, and a lot of that, of course, goes into rich graphics, rich displays, of which increasingly safety content plays a strong role. So gone are the days of just the telltales being rendered on a screen as safety critical content. There's a lot more coming into it around ADAS functions, as Daniel said, the reversing camera with the trajectory overlays. So that's all part of that UX that we look for when we go buy a new vehicle. So that's set to increase, and the OEMs are using that as a differentiator as well. So of course, when we buy a vehicle, we spend a lot of time and dollars thinking about the additional safety features, and those things become a differentiator as well. So I think there are lots of applications today, and it's only set to increase and get richer as time goes on. So what we just talked about is a must-have for today's and tomorrow's vehicles.
Yeah, and I'll add to that. And there's, I think, easy examples to draw on, right? Like wing mirrors are becoming digital displays these days. So there's vehicles transitioning to pillar-to-pillar displays where the wing mirror is in the very far left and far right of the vehicle. If you want to display any type of content on a wing mirror, right? That I know, like traditional wing mirrors, that may have alerts like a vehicle or blind side warning indicators. There's all types of content that could be used to augment those displays, and that's just one example. all of that will have to be considered as safety HMIs.
And of course, head-up display as well, taking another
Yes.
learning from the avionics industry, where head-up displays are used everywhere. We're seeing those come into vehicles more and more, albeit in the premium brands right now, but inevitably that's going to waterfall down to the mass market.
Which will marry with augmented reality, and that makes it even more exciting in the car journeys.
No, absolutely, absolutely. And you touched a bit on that in the presentation then, and just now, Neil, on the avionics industry. And I know we spoke about that a bit in the presentation. I'd like to hear a bit more here about what other kind of insights you can share with us from your journey on safe graphics within the avionics industry, and any and further applications here. Is there anything else you'd like to kind of deep dive into there?
Yeah, there's a lot of parallels because as I said, that we've moved from gauges to glass displays. Those glass displays are now showing more and more rich information. Of course, I didn't mention it in the presentation earlier, but mixed criticality is a thing in avionics as well. There's safety critical data and there's non-safe data. So again, another very strong parallel between the two. Increasingly, we're seeing safe AI come into the avionics industry as well. So one great example we've got that's actually deployed today is automatic air-to-air refueling. So it's a military application, of course, but historically those air-to-air capabilities were done manually. There's somebody with a joystick trying to connect the two planes together, which is quite an interesting experience. We now have that flying fully automated, and of course that uses safe AI to do that. So again, we're seeing safe AI coming into the domain. The last thing I'll say is, of course, autopilots have been a thing in avionics for decades, and here we are trying to solve the same problem for autonomous vehicles. So albeit very, very different use cases, because there are a lot fewer things to bump into when you're at 30,000 feet versus driving down the high street. But nevertheless, safe autonomous systems have been deployed for many, many years in avionics, and that's exactly the problem we're trying to solve with within automotive.
Oh, absolutely. And turning now kind of onto the hardware side, right? We mentioned around the Mali G78AE. What I'd love to hear first, I guess, from probably Jay, and let's start with you first.
Yep.
We've had a couple of questions on this. Is kind of why is this so unique as our hardware IP? Why is this G78AE so unique? I'd love to hear about that, and then I guess Daniel and Neil, please do join in on this as well. But Jay, let's start with you first.
The simplest answer is because we learned to the partner feedbacks, and back in 2018, 2019, we literally had face-to-face meetings with a lot of partners across supply chain, including some of the OEMs and tier ones and silicon partners as well, who explained their particular requirements. And it was a process we followed, and we tried to come up with some of the ideas which were validated with the partners. And as such, we have a product which supports the use cases demanded by our partners through hardware separation and flexible partitioning. That's the basic answer I have. But Daniel and Neil, please plug in.
Yeah, I'd like to add to that. I think we can see today in the automotive industry, there's SoC designs with multiple GPUs, discrete GPUs on them.
Yep.
And those were done strictly to ensure freedom of interference, from not having to share the device between multiple partitions. And this concept of flexible partitioning, right, came from that, trying to solve that problem, right, where before silicon partners would have to size their GPU, pre-silicon, right? And so in the layout of the design, this concept of flexible partitioning allows you to right size your GPU for your partition at system integration time rather than at SoC, layout and manufacturing time. So it's best of both worlds, right? Flexibility and gives you the ability to do safety cert as well.
There's another.
Sorry, carry on.
Sorry, Jan. I was going to say there's another really, really important point, which is around supply chain, which is of paramount importance to the automotive industry. we've got G78AE that's going to be integrated into multiple SoCs from multiple vendors, and that has two benefits. Firstly, you can of course build and support your software stack across multiple SoCs, which can have the benefit that if you're a big OEM where you've got entry-level models right up to premium brands, you can essentially have the same software stack that builds on all of those models, and that gives you a better total cost of ownership for your software stack. The other thing, of course, is you can pick and choose based on silicon availability. So as we've all seen over recent months and years with the availability issues around semiconductors, I'm not saying this is a silver bullet, but it does give you some freedom and some flexibility as well to go with silicon that's available with maybe a lower impact on software changes.
Amazing. Thank you, guys. Really, really great panel discussion here. And just before we get to the audience questions, which I'll do in just 1 second before I've got one more question. If we're getting quite a few questions come in, which is awesome, make sure that if you see a question on there, you think, oh, I like that question, I'd like that to be asked first, just hit the little thumbs up button in the bottom left of the question, and I'll get to those first. So Jayan, I just want to ask you one more question, but again, panel, please join in on this. Is, if you look at the G78A that we've just spoken about, it's pretty scalable, right? But what's the would you be able to share an example with a particular use case for, let's say, surround view monitors, right? In this, how many shader cores are required for a GPU to support these surround view monitor applications? Is there a kind of indication you could give on that?
Yeah, I'll take that one if that's okay, Jan.
Sure.
Yeah, sure.
Yeah, we've had several partners ask that exact question, right? And so we did some benchmarking on it, and there's several use cases and partner, even commercial surround view monitor applications where we've been able to run a surround view monitor at the frame rates they require for their commercial product with as little as 1 shader core. Right, so very, very performant, as small as 1 shader core. But all surround view monitor applications or algorithms, they're not created equal, right? So you really have to do a little bit of benchmarking and to make sure that that's the right size for you. But the nice thing is that this GPU gives you that flexibility, right? It could be as little as 1 GPU, I'm sorry, 1 shader core, or you can add an additional shader core if that's what's required for your use case. So great question. Anything to add maybe, Jan?
No, I mean, you've captured it really well, Daniel, so thank you.
Brilliant, thank you. Let's get on to the questions from the audience now, and do keep them coming in. We've got it to about 10 minutes, where we should be able to get through these.
Sure.
What commercial RTOSs does ARM has ARM enabled or plan to enable for hardware virtualization on G78AE?
So as far as safety critical driver is concerned, out of box, we will support AutoGrid Linux, and then the partners will have the freedom to port it to an RTOS of their choice. And it is in this regard, partners can approach CoreAVI's services business, and CoreAVI will handhold the partners to make sure that the safety critical driver is ported to specific platform and specific RTOS.
Yeah, and I can add to that as well. Sorry, Daniel. Yeah, we work with all of the RTOS vendors out there. So porting our drivers to QNX or VxWorks or Integrity or any of those popular OSs. In fact, we've done proprietary ones as well for certain customers. So it's very very normal for us to do that porting activity for a given RTOS.
Absolutely, and I guess there is a question about is VxWorks enabled. So I don't know if anyone wants to add anything further on that, but I think we just covered it.
Not out of box, but as Neil was saying, it can be ported to VxWorks as well.
This is an area where
an additional service.
Yeah. Actually, this is an area that we're having a partnership with CoreAVI helps tremendously, right? They have a rich history in doing these exact portings, right, for those RTOSs in the avionics industry. So the driver architecture is set up quite nicely to streamline that. So very easy to do.
Amazing. Thank you. And we're getting another question here about the ASIL certification. So why do you state that the GPU is certified as ASIL B, but you followed an ASIL D development process? Which of the metrics is difficult to meet?
D is more difficult to meet. So D that we have is on systematic process to say that we have followed the requirements of functional safety certification with our processes. And on top of that, for diagnostics or runtime, to capture the transient errors, we have achieved 95% coverage, which is ASIL beta. For ASIL delta, it is 99. I hope that answers the question.
You might make a comment, Neil, on the fact that the same driver and stack is used in the avionics industry, which aligns a little bit more with the DO-178B standard, right?
Yeah, exactly. So we have a different safety standard in avionics, which, as you said, is DO-178C, which is more of a system level certification versus ISO 26262, which goes down to almost a component level. But we did the same thing. It's what we call design assurance levels. So we have design assurance level E, which is the lowest, up to A, which is the highest. So obviously flight control systems are considered DAO A. But we develop and certify all of our software to an ISO 26262 ASIL Delta level as well, for the same reason. And you probably don't need it for displays and graphics, but obviously if you're doing GPU for an ADAS function, that could well indeed need ASIL D if it's doing brake control or steering or throttle, that kind of thing.
Brilliant. No, thank you for a really, really comprehensive answer on this. And there's another question that's come in around, is it possible to have VK Core SC run on a combination of ARM GPUs and ARM CPU clusters, such as Cortex A78, or does it need to run exclusively on the GPU cluster?
So the VK Core SC needs to execute on the GPU. So it's a GPU based driver. There's a little bit of a CPU dependency. Of course, we've got that ported to support ARM Cortex, because I think all of the SoCs out there are going to be Mali G78AE with Cortex A's and M's or R's as well. But yes, you need the GPU there, and it's developed specifically for G78AE as well, so it won't run on other ARM Malis, because the two have been kind of developed side by side, hand in hand.
Brilliant, thank you for that, Neil. And we've now got a question around no longer needing an FPGA in the display pipeline was mentioned in the talk. Which piece of the enablement specifically removes the need for this?
So maybe I should clarify, in the applications that we used or we looked at in avionics, the FPGA in that particular case was only doing pipeline checking, so nothing else. So of course, if you've got an FPGA doing other functionality, you can't remove it from that perspective. But yeah, it was doing the pattern monitoring. So as the GPU generated test patterns and passed those into the video pipeline outside of the display area, the FPGA would check for that. Using TrueCore, you don't need the FPGA to do that, because TrueCore does the periodic testing directly into the GPU. Goes off and does the built-in tests or periodic testing of the GPU directly. So the FPGA is not needed. So the GPU output goes straight to the display at that point. I should say
thanks Neil, for that. And
I was just going to clarify. There's actually a white paper that we've got, which is on our website, that goes into a lot more detail of the different use cases as well. So if you have some more detailed interest, then you can find that white paper as well.
Awesome, thank you. I don't know if you've got that to hand at all. You're able to paste the link in the chat. I know the next question is probably for you, so I don't know if you've got it. If not, as you say, people can go to your website and find it pretty easily. I'm sure. So final question we've got in is, the architecture reported by Neil had an FPGA to detect anomalies, but is this just on the data sent to the display? What about faults in the connection with the display or the display itself? The picture related to avionics was showing two complementary displays driven by different components for full redundancy. Just wanted to ask that.
Yeah, it's a good question. I guess in that application, there's an assumption that everything that comes out of the FPGA gets rendered correctly as well. The display may have its own test mechanisms, its own periodic testing to check that once you come out of the FPGA, that indeed nothing's gone awry between there and putting the pixels on the screen. So again, I think that's a use case specific question, depending on what the application and how robust you need to be. At some point, you've got to make an assumption that if it's gone down the wire that far, then it's probably rendered correctly. But again, it's very use case specific. So you may need other mechanisms as well.
And there's an assumption also in our slides that the full end-to-end safety capabilities, right? You have a safety certifiable driver for your display controller as well, right? So that's regardless of how you implement your system, right? You got to make sure you have those integrity checks all the way to the display, and then decide what your safety mechanisms and your safe state is based on any integrity issues.
Brilliant. Thank you both for that great answer. So we're just coming to the end of the talk, but what I'd love to do is before we wrap up is just to get a final word from each of you, any key takeaways you'd like to share with the audience or anything else you'd like to share. So Jane, let's start with yourself.
Yeah. I think I want to revisit one of the questions here, which was very interesting.
Please do. Yeah, let's go for it. Go for it.
So does tier 1 OEM purchase G78AE driver from ARM or CoreAVI for safety deployment? So I'm going to answer it on behalf of ARM and CoreAVI. We have a joint licensing agreement. As far as automotive is concerned, ARM will be the sole distributor of safety critical drivers in automotive industry. And for avionics industry, it will be CoreAVI. Depending on which partner and which industry they come from, they'll have to choose between ARM and CoreAVI. At the end of the day, we'll still be talking to each other.
Yeah, and I can reiterate, it's obviously a close collaboration. And of course, we're looking at taking SoCs from, with G78AE into the avionics industry as well, because it's very, very relevant for that space.
Yeah, absolutely. No, thank you for that. That's really, really great. No, absolutely happy to do that, Jay. And so let's go back to yourself on this. Any final words of key takeaways or anything for the audience today as we're coming to the end of the Tech Talk?
So a key takeaway is we are in an exciting stage and we have an exciting product. ARM and CoreAVI are doing thought leadership here for the automotive industry, and as such, we will be, over the years, see this demand generated into a real need. But yeah, we are at the front end of this cutting edge technology right now.
Absolutely. And Daniel, how about yourself? Any final words for our audience today? Any key takeaways you'd like to share?
Just one thought. I think it's exciting times for all technology companies in this automotive industry, right? And I think it's incumbent on us and anybody in the supply chain to really consider if there's a safer way to do something. Then I think we have to do it, right? Just to build consumer confidence in the systems, these autonomous capable systems that OEMs are deploying.
And finally, Neil, how about yourself?
Yeah, I think ARM's ability to deliver world-class, in this case, dedicated, fit-for-purpose, safety-critical GPUs, and our proven pedigree in the avionics space, it's an excellent collaboration, which results in time to market, reduced risk, time to certification for our collective downstream customers and the ecosystem.
Fantastic. Thank you all so much. And thanks, audience, for your great questions. I really look forward to seeing you at next week's Tech Talk on June 20th, 4 p.m. BST, 8 a.m. Pacific time. Neil, Daniel, Jayant, thank you so much for an awesome Tech Talk today with some really great insights. And I love the little panel discussion at the end. That's always really great. And of course, some fantastic questions from the audience too. So that's it for today's Tech Talk. We look forward to seeing you next week at the same time for another installment of our series where we're talking all about the latest trends, technologies, and best practices from ARM and our ecosystem. Jayant, Daniel, Neil, and the team, thank you ever so much today. We'll see you again soon. Thanks, everyone.
Thank you.
Thanks.
Cheers.
Bye.